Good morning, everyone. Welcome back to Math 115. So yesterday we had the exam. Sorry? Oh, okay. Yesterday we had the exam. Today we're going to move on with new material. So we're going to cover section 3.4. So we've been talking a little bit about exponential functions and logarithmic functions. And what we're going to talk about today is solving equations involving exponential terms or logarithmic terms or both. So today is going to finally be the motivation for why we are interested in logarithms, basically. So let me say a little bit about that, and then I'll go back. So why are we interested in logarithms? Because we have all sorts of equations like this, where we want to know what x should be if it is in the exponent, okay? What exponent should we use here in order to achieve this number? And the way we figure that out is by using logs. So we're going to see that in a minute. But that's where we're going. So regarding your homework, I have a homework for 3.2, which is going to be due tomorrow. So that homework is due tomorrow. I'll post a homework 3.3 and 3.4 coming soon. They'll probably be due on like Tuesday or something like that. Your next assessment is no longer the exam. I guess I should look up when your next assessment is really quickly so I can write it here. By the way, if you want to see the full list of all of the assessments that we're going to have and all of the dates, they're on the syllabus. Looks like Quiz 5 is going to be Thursday, October 27th. So Quiz 5 is 1 week from today. I'll let you know what sections are going to be on that soon. Probably it'll be like 3.2 to 3.4-ish. Something like that. Maybe 3.5. Always better to walk it back than walk it forward, right? Okay, so that's your next assessment. Oh, thank you. Sorry. I also put it in the wrong spot. So it's going to be 3.2 to 3.5-ish. Okay, so that's your homework. That's the quiz that's coming. The exams, I have marked the exams, but I haven't tallied them yet. So I should have those grades in probably today or latest by tomorrow. And then I'll give back the exam papers next week. I still have some students who need to take the exam. So my office hours are going to be today, okay, from 2:30 to 4 p.m. in LeConte 439. So if you want, you can come to my office and we will do like a lot of problems from your 3.2 homework, okay? So you can get a lot of them knocked out with my help and get them done before it's due tomorrow. Okay, so that's my office hours. Are there any administrative questions or concerns before we start in on content for today? All right, it doesn't seem like there are, so I'm going to go back and remind us what we talked about last time. So last time I basically reiterated these log rules, okay, which are going to continue to be really important for today's section and just moving forward in general, okay? So these log rules are going to be important mostly because Rule 3 is especially useful. It is especially useful. What does it do? It allows us to get something that was an exponent, okay, and write it as instead as a prefactor. Why is that nice? Because if we want to solve an equation where the unknown is in the exponent, we're going to use logarithms to get it out, okay? So this is why this rule will be especially important, but the other ones are going to continue to be important as well. Okay, so the log of a product is the sum of the logs, and not the other way around, by the way. That's a common mistake. Log of the quotient is the log of the difference, or the difference of the logs, excuse me. Okay, so these are the 3 rules about logs that you should memorize. We talked a little bit more about them and how to use them to combine logarithms, how to use them to expand logarithms. Yeah, we saw expanding first and then combining. And then we talked about half-life, okay? So half-life was the amount of time needed for a substance to decay to half of what it was before. Okay, so this lies in a class of problems regarding exponential decay or exponential growth, where the rate of growth or the rate of decay depends on the quantity of substance we have, right? Another version of that is, of course, investing, right? The amount of interest we're earning depends on how much money we have in the bank. Or we're going to see another problem today regarding population. The amount of people being born depends on the amount of people that there are alive who are having children, right? So that's what we're going to see today. And that's going to be in the context of solving exponential and logarithmic equations and inequalities. Okay, so I'm going to go over 3 ways in which we solve exponential equations. Okay, and then we're going to have a partner practice where we're going to work on a real-life problem. Okay, so let's talk first about how we solve exponential equations using the same base. So far, the only thing we know how to do is we can solve some exponential equations when we have something like this, right? If I have something like 5 to the x equals 25, we were able to solve something like this by guessing, basically. We can check, well, it looks like 5 squared would be 25, so x should be 2, right? That's what we have so far. But here's another way which we can kind of expand this class of equations, okay? The real reason that I understand how to do this is that, well, we can rewrite this equation as 5 to the x equals 5 squared. So if you can write one side as 5 to a power and the other side as 5 to another power, then because the exponential function is 1 to 1, i.e. it passes the horizontal line test, then the exponents have to be equal. So here, since we get it to here, we can then deduce, okay? We can deduce that x should be equal to 2. So if we have the same base equal to the same base, where the power is one thing on one side and the power is another thing on the other side, those 2 powers must be the same, okay? There's no way to get like 5 cubed equals 5 squared, right? It's always 5 squared equals 5 squared. So the power here is going to be equal as long as the base is equal, okay? So we can use that to solve other equations like the following, right? We can rewrite certain things using the same base. So my goal is to get this down to something like some number to some function of x, okay, is equal to that same number to maybe a number or something like this. Or even another, or we could also have another function of x. That's fine too, because all we're going to do at the end of this is set the powers equal to one another. So in this case, what I want to do is get the same base. So on the right side, I can write this as 5 cubed. And you can see that the left-hand side is going to be written as a power of 5. It's just a question of what that power is going to be. So I have to be a little bit careful here, because what am I doing? I'm taking 25 to the power x. What I want to do here is rewrite 25. Okay, I rewrite 25, but when I do that, I of course need to use parentheses. Okay, why do I need to use parentheses if I'm going to rewrite 25? Because I'm supposed to take this whole thing to the power x. So if I rewrite it as a composite something, right, I need to make sure I use my parentheses so that I take the whole thing to the power x. So these two things are equal. So can I simplify the left-hand side a little bit? What am I supposed to do with the powers when I do 5 to the power 2 all to the power x? You multiply the powers. So in this case, What do I get for the power?
2x.
Just 2x. And the other side is 5 cubed. So what can we conclude? What may we deduce? The base is the same. So what new equation can we get? 2x plus 3? I think 2x equals 3. Yeah. Yeah, 2x equals 3. Very good. I think you had the right idea. So 2x equals 3. Okay, because we have the same base being raised to a power, the power must be the same. If the number is the same when I take it to 2x versus when I take it to the third, then 2x has to be the third power after all. Okay, so that's how we get 2x equals 3, and now we can solve for 3 halves. Okay? So this is how we can do these types of equations. Are there any questions on this first example? Yeah, again, you're going to notice this basically only works when this number and this number are different powers of the same base, okay? So same deal on the other side. What do we get? 9 to the x equals 3 to the x plus 1. Well, we can rewrite this as 3 squared to the x equals 3 to the x plus 1, and therefore 3 to the 2x equals 3 to the x plus 1. And what's my new equation going to be? I have 3 to a certain power equals 3 to a different power. But are these powers really different? No, they're not different. They must be the same. So we get x equals just 1, right? Subtract x from both sides. All right. So that's solving exponential equations using same base. It's just a little bit more complicated version of what we've already done with this 5 to the x equals 25 type of thing. We can expand that to a slightly larger class. But this is not going to help us solve anything like 5 to the x equals 3 squared. Something like this, there's no hope for using this method because 3 cannot be written as a power of 5, and 5 cannot be written as a power of 3. And neither of them can be written as a power of something smaller than that. Okay? All right, so now let's see how we're going to deal with that. Well, first of all, are there any questions on solving exponential equations using same base? All right, it seems like that's clear. Let's talk about solving exponential equations using logs. So I've told you for a long time that logs are really useful, and I never really showed you why yet. But now we're going to see why. So now I have an equation which looks like this, right? 5 times 2 to the x minus 3 is equal to 17. So it's not easy for me to see what x should be, okay, because when I look at this, I think, well, crap. I'm going to multiply 5 times the power of 2 and get 17. The powers of 2 that I know would be like 5 times 2 or 5 times 4. But already you can see 5 times 2 is what? 10. 5 times 4 is 20. And my number that I'm supposed to get is somewhere in between, which means I need a power of 2, which is somewhere between 1 and 2, right? It's going to be something like 2 to the 1.5 power or something like that in order to get 17, right? So now it's not easy to see. I can't rewrite the right-hand side as a power of 2. I can't rewrite the right-hand side as a power of 2 because 17 is prime. So I'm a little bit hosed here until I remember that I have the log rule. And the really important log rule that we learned was that log of m to the r is equal to r times is equal to r times log of m. Okay, where I'm omitting the base here because it could be any base you want, okay? Any base you want. All right, so what are we going to do here? Well, you'll notice one thing needs to be done before we can apply this. Okay? There is a simplification that needs to be done on this equation before I can go ahead and just plug both sides into the log. Does anyone see what I need to do before I can go ahead and take the log of both sides? Yeah, divide by 5. Can you explain a little bit about why you want to divide by 5?
I was just trying to
Exactly. What does it look like here? We have something like m to the r, not n times m to the r, right? If you have n times m to the r, okay, then you got to get rid of the n first so that you can apply the rule. Okay, so Ashley's got the right idea. We're going to divide by 5 on both sides first. So first I'm going to do 2 to the x minus 3 equals 17 over 5, which luckily I wrote down before that this is going to be 3.4. Okay, so now I'm in a position to apply this rule. So I am going to take the natural log on both sides. And you might say, well, why not log 2? Because we have a base 2 here. Well, not log 2 because I don't have log 2 on my calculator. So I'm going to do ln on both sides. And this just looks more complicated than it was before until you remember that the power can come down. Now, the power is going to come down as an x minus 3. That's the power. The entire power, r, must be multiplied times log m. So we put it in parentheses. And then we have ln of just 2 is equal to ln of 3.4. Now from here, we want to get x by itself. And we've done the hard work already. We got it out of the exponent. And from here, it's just a linear equation, right? I'm going to divide both sides by ln 2. So I'll get x minus 3 equals ln of 3.4 over ln of 2. And then that tells me x equals whatever that number is. Plus 3, right? Okay, so you can type this in on your calculator. You'll do ln 3.4, you'll get a decimal. You'll do ln 2, you'll get a decimal, which is negative, I think. No, not negative. You'll get a decimal, which is positive, and then you'll divide those two numbers, and then you'll add 3 to it. Wait, ln 2. 2 to the e to the... Oh, okay, it's because we have minus 3. Okay, yes, okay. So yeah, that's what it should be. Okay, so this is how we solve using logs. We basically just use this one rule. Okay, this one rule helps us to solve exponential equations because we can plug into the log and that gets the exponent out of the exponent, basically. Okay. So one thing that I'll mention is that a lot of students get a little bit tripped up at this step, okay? At this step, they say, well, it's confusing to me because we've got ln 2, okay? We've got ln's of stuff floating around. But what I want you to remember, okay, is that this is just a number, okay? We write it like this, but it just means a number. It's some decimal, right? And this is also some other decimal, okay? And I have no doubt that you would be able to easily solve an equation like this. X minus 3 times 5 equals 7. Something like this, I think you would have absolutely no trouble solving, right? All we would do is just divide by 5 on both sides and then add 3. Yes? Something like this would be really easy for you to solve. But some students, for whatever reason, the ln's being here trips them up. So I just want to impress upon you all that when we write ln of 3.4, it's just another way of writing a number, which is a number something like 1.235, whatever, something like that. Some kind of decimal number. But it doesn't have a nice way of writing it. The nice way of writing it is to write ln of 3.4. Okay, so that's how we write it. Is that clear? Okay. So this is why logs are great. So I'm just going to put here, these are just numbers, okay? Just numbers. So we're going to treat them just like how we would any other number, okay? All right. Any questions on that example? Yeah.
When you get the final answer, is there any preference on number of decimals?
On what, sorry?
So like the final answer, so if you plug that into a calculator, you say you get like 4.7 blah blah blah.
Mm-hmm.
Is there any preference on the number of decimals that we use?
Oh, okay. So I'd honestly prefer you to leave it like this. Okay, so the question was, how many decimals should I take it out to? Well, you're going to notice both of these numbers have like an infinite number of decimals. They're going to be like irrational numbers most of the time. So, yeah, I would prefer you to leave it in this notation, honestly, because this is more clear than giving me a decimal which goes out to like even 100 decimal places, right? Because this includes all the information. So yeah, I prefer it like that. Good question. All right. So this is going to inform one other thing that we do, which is solving with different bases. Okay, so like I said, we can't express 3 as a power of 5 or 5 as a power of 3. So we're kind of hosed until we do the following. Well, we just have the thing that we want to know is in the exponent. So what are we going to do? Yeah, natural log. If the thing you want is in the exponent, you got to take the log. It's pretty much always what you're going to do. So we do log on both sides. And we get what? 2x minus 3 times ln 5 is equal to x plus 1 times ln of 3. And now again, this is nothing but a linear equation in x. This is a linear equation in x. You've been solving linear equations in x since like the 6th grade. So I think what makes this so confusing is, again, the presence of the ln. Okay, the presence of the ln is what makes this a little bit tricky. Okay, so what are we going to do? Sometimes I find it helps students to write a similar equation like 2x minus 3 times some number, right? Like 6. And then equals x plus 1 times a number 3, right? How would we solve an equation like this? What we would do is distribute, right? We would distribute, and then we would get all the terms with x on one side, and then we would get all the numbers on the other side, right? And then we would divide both sides by whatever this number is, yes? That's what we would do to solve this linear equation, okay? So I don't want anyone to be confused just because there's a presence of ln's here, okay? So let me show you how we will do this, okay? All we're going to do is the exact same thing. We're going to distribute out. So I get ln of 5 times 2 times x. I should have left more space. I'm going to erase this, and we're going to go down instead. ln of 5 times 2 times x minus ln of 5 times 3 equals ln of 3 times x plus ln of 3. Okay, so now I'm going to do the same thing. I'm going to get all the terms with x on one side, and I'm going to put all the numbers on the other side. So I get 2 ln 5 of x times x, and then I get minus ln 3 of x, not of, Jesus, times x. And then I add ln 5 times 3, so that's 3 ln 5 plus ln 3. Okay, so this has the form ax plus bx equals c, okay? ax plus bx equals c is basically what this form is. So what do we do? How would I solve the equation 2x plus 3x equals 5? How would I solve this? The first step would be to do something here, right? What would I do here? Combine like terms, right? I would combine like terms. How do I combine 2x and 3x? You just add 2 and 3. So what is this? What is the rule here? The coefficients get added, right? Okay? So we combine like terms here. We have a number times x plus a number times x. We combine them by adding those two numbers together and then multiplying with x. What do we have in our equation? A number times x minus a number times x. We can combine like terms here. The only thing is, here it's really clear that this becomes 5x because 2 plus 3 is 5. In this case, we're going to have to write it in this kind of a shape, okay? Because there's no easy way to write what do we get when we subtract ln 3 from 2 ln 5, except in the most obvious way possible, which is 2 ln 5 minus ln 3. Okay? So, this is a term with x, this is a term with x. The way we combine two terms with x is we add or subtract the coefficients. Okay? So I know this looks scary, but there's no difference between this and adding together 2x and 3x. So I hope that makes it a little less scary for you. Are there any questions on how I did this step? Because this is really the crucial step here. Okay, then if not, we just set that equal to ln 3 ln 5 plus ln of 3. Okay, and now what is my equation? My equation is as simple as can be. This equation is a number times x equals a number. You love solving equations like this, like 3x equals 6. What do we do when we solve an equation where we have a number times x equals another number? We want to get x by itself, so what should we do? Divide by this number. Okay, so for example, 3x equals 6. We divide both sides by 3 to get x alone. Here we have just a weird looking number, okay? But the process is exactly the same. We have a number times x equals another number. How do we solve an equation like that? We divide both sides by whatever is being multiplied with x, which in this case is the weird looking number 2 ln 5 minus ln of 3. So we cancel this entire number here by dividing it. And if I divide by that number on the left side, I must divide by that number on the right side as well. So we get 2 ln 5 minus ln 3. All right, so in the end of the day, we get x equals 3 ln 5 plus ln of 3, all divided by 2 ln of 5 minus ln of 3. Okay, that's a good question. So the question is, can I do the following? Well, here's an ln 5, and here's an ln 3, and here's an ln 5, and here's an ln 3, so I just cancel, 3 halves. Is there anything wrong with doing that?
It's added and subtracted and not multiplied.
Yeah, so I think the only time that we could cancel something like that is if we were to take a GCF out of each of the bottom ones. So if we had something like, so you can think about it this way, right? 3 plus 2 divided by 3 minus 2, right? What would you get? I mean, if you just cancel, there's nothing left, right? Or if you want, you could say it's 1, 1, 1, 1. This is all very wrong, though. So this would be, what, 2 over 0, something like that. But we know that's not true. What is 3 plus 2? 3 plus 2 is 5, and 3 minus 2 is 1, right? So this is actually not correct. What we can do, though, is if we have something like 8 minus 4 over 6 plus 12, what we can do is we can rewrite this as 2 times 4 minus 2, or we could write it as 4. No, 2. We could rewrite it as 2 times 4 minus 2, and then we could write the denominator as 2 times 3 plus 6, yeah? And then you can cancel these ones. These ones you can cancel. So we can only cancel if we have like a GCF like that, which is present in all of the terms. But these pluses and this minus, this plus and this minus are going to stop us from being able to cancel like that, okay? That's a good question. I find that a lot of students' intuitions kind of go out the window when suddenly we're writing the letters ln everywhere. But it's important to just, I guess, reestablish those same intuitions for these new weird-looking numbers. Okay, so are there any questions about how I solved this example problem before we move on to a partner work problem? Yes?
So how did you get like to 2x minus 3? I don't get, where did minus 3? Oh, wait, never mind. Okay.
So what happened was we wanted to get this out of the exponent ultimately because it's bad when the thing we want to know is in the exponent because it's hard to isolate. So we apply a log. We temporarily make the equation more complicated than it was before in order to move this guy down. So this guy came down and we got 2x minus 3 times ln 5. And then what I did was I did 2x times ln 5. That's how I got this one. And then minus 3 times ln 5. That's how I got this one. Does that answer your question?
So at that end term, should there be like an invisible 1?
Invisible 1.
Like where ln 3 is, like is it technically being multiplied by 1?
Yes. Okay, so on this side, we had x times ln 3. That gave me ln 3 times x. And then when I did 1 times ln 3, ln 3 is just a number. If you multiply any number by 1, you get just back that number itself. Yes, Gavin.
So just for like explaining it in like my head, I guess, this is basically just we're doing distribution property, I guess.
Exactly. This is just the distributive property. Right? What would I do to simplify 2x minus 3 times 5? You would multiply 2x times 5 and get 10x, yeah? And then minus 15. So yes, it is exactly the distributive property. It's just that these weird looking numbers, they throw your brain for a loop, don't they? Okay. But yes, exactly, distributive property. Any other questions on this one? These are good questions. Keep them coming. All right, if not, then try to form into groups, please. If you're sitting by yourself, try to move over and meet with a partner. We're going to work on the following partner practice problem. So, I'll explain this problem really quickly. So, what do we have? We have another weird-looking exponential equation here, or exponential function. So, population at time t is given by this formula, where of course p naught is going to be our original population, r is going to be our growth rate, okay? Our growth rate, and t is the number of years. So if I plug in a value t like 10, then if I do all of this math, it will tell me what should the population be 10 years from now, okay? So here's the information we start with. The USA population is 308 million. What is that going to have to do with in this equation? Probably P naught, right? How about the USA population growth rate is 0.9% per year? That's going to have something to do with R, right? And then here's the question we want to answer. When will the population be 350 million? Okay. When? Yes.
Can we use a calculator?
Yes, of course you can use a calculator. It will be necessary to use a calculator.
I cannot wait until it's a calculator.
I wish I brought mine, like,
Lane, can you form up a group with Ruth and? Oh, you're forming with them. That's fine. Yeah, you can go with them. Yeah, that's fine. Lily, do you have a partner?
Yeah, she's in the.
Oh, okay, gotcha.
Liv, do you have a partner?
You want to work
It would be
Ashley?
0.009.
I'm not sure.
You just threw her name.
So here we just want to get T by itself, right? So first of all, I think
Yeah.
what might be the easiest thing to do would be first maybe simplify.
I think it's maybe
Right,
first
if I add a point zero, or I can just 1.009.
I want to. Because we're looking at the amount of time.
And now this kind of
Well, this is right, it is also like 0 point.
like you have a number on one side.
Oh. You're not looking at how many millions. Less,
Something to account
it's,
for.
hey,
Yeah.
0.009 is 10%, you make it 0%. Just for future, let's sum it up. Just out here. I think we're just like,
I think
And then he might change it.
I'm so smart. Who never thought we were so smart? No, I was actually being serious. I didn't even think about it. I feel like we're gonna have to use law. There's two. I don't know where it's
It's two.
So if we have
No, no, no.
So we take.
It's not 100 million, it's just million.
Divide by 100, so you take 30 and divide by 100, and you get 0.000.
I'm thinking that's.
I can't say it. I don't like context.
You're just off by 1 decimal spot. Okay. Exactly.
1, 2, 3, 1, 2, 3.
Times this thing equals 350.
No, oh, you have this game. I deleted the whole thing. I'm not even going. Oh, it's over.
So,
That's a long ass.
this equation looks a lot like that equation we did at the start, which said
Here we go.
5 times 2 to the something equals something, right?
No, this
We
is-
got
no,
what?
this is the wrong
A
equation.
number times something to the power equals
We're
nothing.
just gonna have to figure it
A
out.
number times something to the power equals nothing. Right? Same form. So we're gonna apply the same type of logic. What do we have to do here? We wanted to use this rule here, which says that the m to the r is 1, right? Oh, we couldn't quite apply it right at the start, because of that, 5, right? So what are we gonna do here? We're gonna take that 308 away.
We should get that.
Where are you gonna put it? Okay, so.
Look at you go, okay, listen,
When we
you are
have- now we
learning
have
every
something
day
here
your life.
that's like log n,
A number of teams. Yeah.
If we were to take the log of both sides now, that's even come right out. Okay. On the right track?
So then we're gonna divide through.
Yes, hopefully.
How's it going over here? All good. Are you all done? Yeah, I don't know what the number is, but let's see if we're here. Okay, there's one small issue here, which is if we have a percent, if we have a growth rate as a percent, well, what is like 5%? What should we plug in for R? If it was 5%, R would be not 5, but 0.05, right?
Oh, it'd be
So if we
zero,
have,
zero.
yeah, so if we have 0.9%, what you wanna think of is percent as meaning, per meaning divide, cent meaning 100. So 0.9%, we need to take 0.9 and divide by 100, which would give us 0.00.
We are gonna have.
How's it going here? All good?
Dude, literally, that's what, I'm on that track.
Good. And then we just take the ln on the side, right? So we get a t, and then.
Maybe we're rounding our
Going over here. What do we do wrong? Let's see, come on. I like this first move, right?
Okay,
We divide
so
both
this
sides
is
by
right.
308. And then we have,
So we're gonna put this in the
okay,
log.
so I think there's just a little bit of confusion here with what the ln is. So the ln isn't actually being multiplied here. It's actually what we're gonna do is we're gonna take this equation, which says what, 350 over 308 is equal to 1.009 to the t, right? That's what this equation says, yeah? So, what we're gonna do is not multiply by ln, we're actually going to plug both sides into ln. So here's how that would work.
So like,
ln of 350
using L
over 308 is equal to ln of 1.0009 to the power t here, right? And then what does this power t do? It comes down front, right? So then we get ln of 350 over 308 equals t times ln of 1.009. Yeah? Okay, so I think, I'm not really sure what happened from here to here. But what we want to do is actually, we want to plug in both sides of this equation into the function ln. So if I have two numbers which are the same,
Seven.
if I plug them into a function, the outputs will be the same, right? Because these two numbers are the same, so if I plug them both into the ln function, we'll get the same result as an output, yes? Okay, so from there, what do I have? I just have t times a number equals another number, which is divide, right? Make sense? Are you good with that, Layton? Okay. How's it going up here? It's going.
Trying to go.
Alright, can I take a look? Okay, so let's, that looks like a good R value. I like this equation a lot. And then, okay, from here to here, I think there's a little small thing that we should do first. Okay, so if you go back to our example here. I think here. Remember when we had an equation like this? This looks like what? A number times another number to a power equal to our equation is just like that. Right? We have a prefactor times a number to a power equals another number. Right? So what do we want to do in this case? We wanted to apply this rule, right, which says log MR equals like this, right? But what do we have to do first in order to apply that rule? We had to get rid of the 5, right?
So we got.
Okay, so the reason we gotta get rid of the 5 is because the rule only applies when we have something to a power. If this 5 is here, and the 5 is here, this power is here. What we have to do first is get rid of that. So on our equation,
Stop at 8:30.
We're gonna divide those sides by 308. And then we're gonna get not ln 350 or ln 308, but we're gonna get something like ln of
My mom plays.
355 by 308. Okay, do we need a little bit more time for any groups? You need a little more time?
Yeah, we need to know. Okay,
We're kind of lost.
yeah, we're like lost in the park. See, look what it says, see? Trying to read it upside down or something. Oh, is it pink?
The test and looking schedules on it.
Okay, this is what you get when you divide 350 by 308, right?
Yes.
Okay, this is good so far.
See, dude, I was there.
Well, where you went wrong is, okay, here we have this number on this side, and t times this number on this side.
Wait, whoa, stop.
You like what I had without us.
Yeah, I know. This was good one, Lou. I don't know, but.
I know the joke. No.
Here, we have a number. Oh, wait, where's this? Exactly. And now you start doing all that.
Okay, where do I go from here?
Someone was told me about okay, so
I just was there. So elevations
yes, this looks like this. Once you do this, all right, so let's come back together as a class. We're gonna discuss this one. So I saw all sorts of good math going on out there. Great job, everyone. So we can do this in a couple of different ways, okay? So you can let's first think about P naught, okay? So the original population is 308 million, right? So you can think about this function as expressing population in one of two ways. You can put that P naught equals 308 million, like so. Or you can think of, well, I can just say that this population function is going to describe not the USA population, but rather the US population in millions or something like that. So you could also say P naught is just 308, right? You can do that as well. So two different ways. What about if the growth rate is 0.9%? So should R be 0.9? No. What do we do when we have a rate? That's okay. I saw a lot of people had something like this. If I have 0.9%, what do I need to do to that number to get the R value?
Divide by 100.
Divide by 100, right? Percent, per means divide, cent means 100. Divide by 100. So we take 0.9 and divide it by 100. If we do that, we get not 0.9 but 0.009. This is our R value. So P of t is going to be equal to 308, I'm going to choose this method, times 1 point, okay, it should be what? 1 plus 0.009 to the t, right? And I can simplify that a little bit to just 1.009 to the t, yes? Okay, so this is the population after t years. And my question is, how many years, okay, in other words, what is the t value that I need to plug into this function such that if I plug in that t value, I get 350 million as the output? Okay, 350 million as the output. That's what I want to know, is what is the t value that I should plug in here such that if I do this and I put that t value in as the power, then I multiply all that out and I get the number 350 as my answer. Okay? So from here, it's just like the one we started with, right? It's just like the one we started with here. When we did this one, we wanted to use the log rule, right? We wanted to use the log rule, which says log m to the r equals r times log m. But there was one thing that was causing us a problem here that Ashley helped us resolve, right? Which was I can't just go ahead and use ln right away. The reason I can't use ln right away is that I want to bring this power down. But I can only bring that power down when this guy is by itself. So the first thing I have to do is get rid of this pesky 5, right? So what do I have? I have a prefactor times a number to a power equals another number. In our equation, what do we have? Oh look, a prefactor times a number to a power equals another number. Same exact process as that example. We're going to get this guy by itself so that when we take the log, the t will come out. Okay, so that's what we do. So we get 1.009 to the power t is equal to 350 over 308. And now what do I do? Now I have it by itself. Now I can use that rule, ln of m to the r equals r times ln of m. When we use this rule here, we get ln on both sides. So what we're doing now, okay, is not multiplying by ln. We're going to take these two numbers. These two numbers are the same. If I plug both of them in to the same function, since the input is the same, the output will be the same. Okay, two numbers are the same. If I plug both of those numbers into the same function, I get the same output. Same input, same function, same output. So this is what we're doing. We're plugging in. Like so. And now the t can come out, right? Okay, so now I have something which looks like t times a number equals a number. So how do I solve? I divide by the number which is being multiplied, right? I undo a multiplication with a division. So I get t equals ln of 350 over 308, all divided by ln of 1.009. And someone tell me what you get when you do that? 14.2. Okay, 14.2, something like that. I'm taking your word for that. Oh, it's your word. Well, I'm taking Chris's word for it then. Did anyone get a similar answer? Or something different? Yeah, you got the same thing? Okay, good.
I thought he was about to say something. I was like, oh.
Nope, I got something different here.
Sorry, what was
Is
that?
it okay if we go like more decimal places?
Is it okay if you go more decimal places? Sure. In fact, what I really should put here is not an equal sign, but an approximately equal to, right? That's what I should do. Okay? So on an exam, I would ask you to leave your answer like so, okay? Because I'm not going to have you plug it in on a calculator. It's just I believe that you know how to plug in on calculators, so as long as you can get here, I'll be happy. Any questions on this example? What is so funny back there?
They're just like giggly silly dude.
They are. Okay, well, this is this example. So what I want to impress upon you is the usefulness of logs is really coming in when we want to know what the exponent is. If the exponent is unknown, we use logarithms to get it out. Okay? So it all comes back to this rule, this power rule for logs, which says that we can take the log of something to a power is just that power times the log. And then, hey presto, we don't have exponents anymore. We paid with logarithms, but logarithms are okay because we can compute them with our calculator. So any final questions on this example before we move on to something new? Okay, if not, then we got about 11 minutes left. I am going to talk about something else.
It's Thursday.
Is that
On
it's
Friday for this class.
it's Thursday, so we can't learn anymore?
That's what I'm thinking.
Yeah, it's
And
now
exam.
it's so cold now right now.
What does the temperature have to do with anything?
This is my vlog.
It
It
is
makes
now.
my brain work.
No, now it's 44.
Not much better.
Now it's
It makes
sun
people
has
work
risen.
slower and not as well. Which is all I want to do. When you're going outside and it's cold, like what do you want to do? You want to go back in bed.
I'm sick.
And
I walk
put
here with
some-
my eyes closed.
No, like actually I was like getting out of bed to go wash my face and I fully like walked to my sink like this so I didn't have to open my eyes.
hmm
No, I get ready
It's
to
bad
go.
out here. It's bad out here. People be not opening their eyes.
Be
It's because this class is at 8:30.
Yeah, I'm not a fan of that either, by the way.
I wake up, I don't have a class till 4:30 every Tuesday and Thursday.
That's ridiculous.
So I wake up
What do you
so
do
nice.
with your day?
I mean, it sounds like what you're saying is you have like, 8 hours of time to study math in between.
I have no reason to do anything, 'cause it's like I'm tired, so it's like go to bed, but then it's like actually, so what
I
do I
have
do?
classes until 12:15.
Like there's no like going back to bed.
Just sitting around.
Yeah, actually I have classes at 45.
That was me yesterday.
Yeah.
All right. We're going to talk about one more thing really quickly, and then maybe we'll leave a tad bit early.
Yay! Surprise!
As long as there's not another partner practice.
There's not another partner practice. Okay. So let's focus up for just a couple minutes here, and then we can head out. I'm just going to do this one example here because I don't want to overload us here. Okay, let's talk about now one basic log equation, okay? So we've seen equations where we have x, which is trapped inside of an exponent, okay? So the way we get it out is using logarithms, right? When we use logarithms, we can get something out of an exponent. And we are able to do that because the log function and the exponential function have a special relationship. Can someone remind me what is that relationship? What is the relationship between the log function and the exponential? Yes?
Isn't it, can't it, like, the second one be transferred to, well, turned into log e of x in parentheses?
Just read the equation.
The second one?
No,
You mean this?
yeah.
So, okay, the relationship that we have between log a of x, the relationship that this function has with the function a to the x is a very special relationship. What is that relationship? Well, this is an exponential function, and this one's a logarithmic function.
Oh, you just read that from there.
Yeah, Ashley said it. It's the word I'm looking for is inverse. These two functions are inverses of one another. The reason that I can use a logarithm to get an exponent out of an exponential is because it is the inverse function. So how do you think I'm going to get x out of a logarithmic function? I'm going to use the inverse, which is the exponential function. So rather than taking the log of both sides, I'm going to plug both sides in for x in an exponent. Okay, so let's see how that works. So these two functions are inverses. So to to get x out of here, what I need to do first is isolate the log, okay? So the first thing I'm going to do is 3 log 2 of x is equal to, what is this, negative 3?
I thought that was.
I couldn't tell what it was.
I thought it was now two.
Oh, it says log, oops, oh god. It says log 2, sorry, bad handwriting. Okay, so now what do? We divide by 3. So log 2 of x equals negative 1. And now what do? I need to do something similar to this, right? When I have this set up, what am I supposed to do to get t out of the exponent? I plug both sides into the log function, okay? Now I have something not trapped in an exponential, but trapped in a log. How am I going to get it out? I'm going to plug it in to an exponential function, okay? So I'm going to do 2 to the log 2 of x equals 2 to the negative 1. So I plug both of them in as the power in this function. And then what is this? How can I simplify this left-hand side? Sorry? Yeah, these two functions are inverses of one another, which means they undo each other. So if I take x and I do something to it, and then I immediately undo that thing, what am I left with? Just x. And then on the right side, 1/2. Yeah, Gavin?
So why'd you put it over 2 again? I'm a little lost over that.
So what I'm doing here is I say these two numbers are the same, yes? If I take two numbers and they're the same number, and I plug them into the function, 2 to the x, I should get the same thing as an output. Do you agree?
Yeah.
So that's why I do that. And the reason I do that is because I know if I do 2 to the log 2 of x, these two things are going to undo one another, and I'm going to be left with just x.
Okay.
Okay? Does that answer your question? Okay. So this is how we solve an equation involving logarithms. Any other questions before we close for today? All right, then we'll stop there.